Oxygen transport in the blood, very simple. Hemoglobin contains 4 subunits. Each subunit, we talked about it, each subunit has 1 heme molecule. Basically, we can try to draw it. So 4 subunits, heme, in the heme there's iron. This is where oxygen binds. So oxygen binds to the iron. Maximum number of oxygen molecules that can bind to hemoglobin are 4. They don't have to be 4. It can be 4, 3, 2, 1, none. It's all good. Now you have to appreciate that different hemoglobin molecules will have different number of oxygens bound to them. This is why we have this sort of average hemoglobin saturation. We call it a saturation, meaning that what percentage of a total capacity of oxygen binding that hemoglobin can do actually bound. So if, say, for 1 molecule of hemoglobin, if there are 4 oxygen bound, 100% saturation. 3 molecules bound, 75% saturation. 2 molecules bound, 50% saturation. As we mentioned before, the hemoglobin can bind up to 4 molecules of oxygen. First of all, it turns out that each subsequent molecule of oxygen binds to hemoglobin easier than the previous one. So first one is kind of hard, second one easier, third is easy, even easier, and fourth is like super easy. This is called cooperative binding. But the big takeaway from what we just talked about is hemoglobin dissociation curve. So hemoglobin dissociation curve describes the saturation of hemoglobin depending on the oxygen pressure. So this is oxygen pressure, this is saturation in percent, and this is how it looks. My drawings are not super good, okay? So remember that that's 100 millimeters of mercury, and the hemoglobin saturation at this point is approximately 100%. Okay, that's important. So basically, all hemoglobin molecules carry 4 oxygens on them. Now, for instance, if we take 40 millimeters of mercury, the saturation of hemoglobin molecules will be on average 75%. Now I want to highlight what it means. It doesn't mean that all hemoglobin carries only 3 out of 4. Some carry 4, some carry 2, some carry 1, some carry 3. But on average, 75% of those irons, they are bound to oxygen. Some of those spots for oxygen carrying are actually empty. So this is hemoglobin dissociation curve. What does that mean? What these numbers mean? At 100 millimeters of mercury, the saturation is 100%. 40 millimeters of mercury, the saturation of hemoglobin is 75%. This partial pressure is in the lungs. So as blood goes through the lungs, practically all hemoglobin is saturated. For our intents and purposes, let's say all. As it goes into the tissues, for that partial pressure, for 40 millimeters of mercury, saturation should be 75. That's what our nature is working. So it has to go from 100 to 75. And that drop, 25%, is what is actually unloading in tissues. So you can see that only a quarter of all oxygen that hemoglobin carries is delivering to tissues. Okay, so this 75%, this oxygen goes back to the lungs. So we only imagine that you have a truck coming in with a shipment, and this truck unloads only quarter of that shipment. Why this is important? Well, actually, if you suddenly stop breathing, you still have a pretty good depot of oxygen bound to the hemoglobin. This situation has another serious implication for us. So what would happen if, for some reason, the pressure of oxygen in your lungs will go down a little bit? So you move from Ohio to mountains of Colorado. The pressure goes down a little bit. Your saturation will be practically 100%, maybe a little bit less. So that gives you some wiggle room. Okay? Now, what is important here? Imagine that you have really active tissue, metabolically. So that is adaptation. Basically, you are adapted. If you go to the higher altitude, you still have a pretty good saturation. Now, what about here? If you exercise, the partial pressure of oxygen in your tissues goes down, say to 20. Okay? Now, what you have at 20, the saturation, I don't know, let's put it at 40%. Which means now that at 20 millimeters of mercury in the metabolically active tissues, the saturation of hemoglobin will be 40%, and the unloading will be not 25, but 60%. So much more oxygen will get to metabolically active tissues. One last bit about metabolically active tissues. As the result of metabolism, oxygen concentration goes down, CO2 concentration goes up. As CO2 concentration goes up, pH goes down. So in metabolically active tissues, CO2 is up, oxygen is down, pH is down. All of these chemical factors will increase hemoglobin unloading, meaning that it will shift the curve to the right. So what it means, if CO2 in the tissue increases, at the same partial pressure, you will have higher unloading. Okay? So that's what we say when we say the curve shifts to the right. So basically the curve shifts to the right in the metabolically active tissues. Oh yeah, and metabolically active tissue also has increased temperature. So these four factors, increased temperature, decreased pH, well, we actually have to remove oxygen from here because that's what. So increased CO2, decreased pH, increased temperature, they all increase unloading, they're all shifting the curve to the right. And quite opposite in the lungs, CO2 is pretty low, pH is relatively high, surfactant is kind of basic, and the temperature is lower because we inhaled outside air. So that's tissues. And what we're going to observe in the lungs, we're going to see lower CO2, slightly higher pH, and lower temperature. And all these factors will shift the curve to the left. That change, that response of the curve, increased oxygen unloading in response to CO2 or lower pH, increased temperature, is called a Bohr effect.